Delaware Tech, Chemistry 110, Vesper theory. So before we talk about Vesper theory, let's go over a few definitions of some common terms. We have central atom, bonded atoms, also known as outer atoms, substituents or ligands, and steric number, also known as domain number. Okay, well, what's a central atom? Well, a central atom is just the atom that other atoms are bonded to. So if you have one atom in the center and there are 2 or 3 or 4 atoms linked to that atom, that's the central atom. And if you have a larger molecule, a number of different atoms can be considered the central atom, one at a time. So you would look at one atom and all the atoms attached to it, and look at the shape of that atom and its bonds. And then you look at another atom in there in order to determine the shape around that central atom. And we look at each atom's geometry independently in order to get the idea of the whole molecule's geometry or shape. The bonded atoms, as the name suggested, are just bonded to the central atom. So, for example, if we have water, H2O, which is really HOH, the O, the oxygen, is the central atom. And we signify the central atom in Vesper theory with the letter A. The H's in this case are the bonded atoms or the outer atoms, and they are also equal to the number of bonded pairs of electrons that link those bonded atoms. In other words, if we have 2 hydrogens attached to the oxygen, well, we have 2 pairs of electrons that make up the bonds of those 2 hydrogens to the oxygen that's the central atom. Now, you'll notice there are some molecules that have double and triple bonds. In Vesper theory, for now, at least beginner Vesper theory, we only count the single bond portion of double and triple bonds. So if you see a double bond, just count it as one pair of electrons or one bonded pair, or just the one atom that's bonded by those bonds, whether it's a single, double, or triple bond. Looking at double and triple bonds in their own right is more advanced, and we won't be covering it in this course. Steric number, or domain number, is just the total number of electron pairs. Again, we're only counting double bonds and triple bonds as single bonds. It's the total number of electron pairs around a central atom. And the way to count that easily is just add up all the bonded atoms to the central atom, because each one of those will be bonded by a pair of electrons, and any remaining lone pairs on the central atom. So we add those up. And the sum of those, so if we have 2, in the case of water, we have an oxygen that has 2 hydrogens, but it also has 2 lone pairs. So the total steric number or domain number for the oxygen in water would be 4. Another example is ammonia, NH3. Nitrogen has a lone pair. So that means we have 3 bonded atoms, X equals 3, and 1 lone pair, E equals 1. And we would designate the parent designation of this molecule using Vesper theory as AX4. In other words, we add the X and the E together to get the actual X value in the parent designation. But the reality is the final designation has 3 X's and 1 E. So we would write it as AX3E1 or simply AX3E. This tells us that there are 4 pairs of electrons around A, the central atom. 3 of those are in bonds to atoms, in this case hydrogen, and 1 pair of electrons is just a lone pair not bonded to any other atoms besides the central atom. So valence theory itself is, we call it Vesper theory. The word isn't actually spelling out the word Vesper. We pronounce this particular acronym this way. VSEPR stands for valence shell, electron pair, repulsion. And this theory was worked out in 1957 by Ronald Gillespie and Sir Ronald Nyholm. And shown on the right here, some of the many shapes that they predicted based on how many electron pairs were around each central atom. And this theory is quite useful in predicting the shape of molecules, especially around individual central atoms. So we look at the outermost electrons, the valence electrons. They're either in lone pairs or they're in bonds. And the idea is those valence shell electron pairs, so that's the first four letters of our abbreviation, repel each other. And they want to get as far away from each other around the central atom as possible. They spread out so that they all have their own space around the central atom. And that spreading out, that repulsion, is responsible for the shape around that central atom, and that will lead us to the shape around in the whole molecule. So what can Vesper do for us? Well, it predicts the mutual repulsion of all electron pairs, whether they're in bonds to other atoms, to bonded atoms, or they're lone pairs. They will all repel each other. They all want to stay away from each other. And that allows us to predict the shape around a central atom, which we'll call A. And as a result, this allows us to predict the overall molecular geometry, the overall shape of the molecule around that central atom. But there are many, many exceptions. You are certainly not responsible for any of the exceptions because they're much more advanced beyond the scope of this course. But it's not a perfect theory, but it works pretty well to predict the shape of the vast majority of small covalent molecules that you will be exposed to. And the reason why we have this repulsion is twofold. Number one, you should already know electrons are negatively charged. If you have one pair of electrons near another pair of electrons, those are negative charges trying to stay away from other negative charges. So they repel each other. Simple as that. But we also have the fact that the pairs of electrons in their own orbitals, remember we talked about orbitals in the last unit, these orbitals filled with electrons cannot overlap one another. They have to have their own volume of space, what we call their own quantum state. So every electron has to have its own state. It has to have its own level, its own type of orbital, its own suborbital, and its own spin in the orbital. You don't need to know these details. Just think of it as every atom, every electron has its own specific address. No two electrons can have the same address, and therefore they can't occupy the exact same volumes of space, except for the fact that two electrons within an orbital can share an orbital, but that's because they have opposite quality, what we call spin. So, what are the steps to looking at Vesper theory? How do you use it? Well, the first thing you do is decide which central atom you're going to consider. In most of the small molecules, there's only one central atom, one that the other atoms are all attached to. You then draw a Lewis structure of the whole molecule, and you look in particular to that central atom. And why are you looking at the central atom? Well, you want to determine its steric number or its domain number. And for that, you look at that atom and you count up how many other atoms are bound to it and how many lone pairs are on it. And you add those together, you get a total, and that will be our domain number or steric number. So we initially count both kinds of electron pairs. We count them as the same thing initially. We'll separate them later, but at first we'll call them, we'll just call the total X, even though one is really X and one is really called E. The lone pairs are called E. But for now, we'll add them together. We'll call them X. We'll treat double bonds and triple bonds as single linkages. So that's a single value of X, not a double or a triple. And you'll get some parent formula, A with a certain number of X's, 1X, 2X. In fact, we know of molecules all the way up to 9, to AX9. In this course, you will only need to know the structures up to AX4. And then you're going to consider the repulsion of all these pairs around the central atom. None of them want to be near one another, so they all spread out as much as possible in 2- or 3-dimensional space around the central atom. And this allows us to predict the shape around that atom. So let's look at some examples. An easy way to illustrate Vesper theory is to tie balloons together, believe it or not. These are the balloon molecules, and I made these in my living room. I just tied balloons together, and think of the knot not the balloon, the knot on the balloon or the center of tied balloons as the central atom, A. And each balloon will represent an orbital with a pair of electrons in it, an electron pair. And sometimes that electron pair is part of a bond to another outer atom, and sometimes it's just an electron pair, a lone pair on that central atom. But in this case, I've shown you examples where we have electrons. They can either be bonded or lone pairs. For now, we're going to consider them all to be bonded. We're just going to consider the bonded possibility. In other words, in the first example, it's A with one balloon on it. It's a knot with one balloon, a central atom with one balloon. The second example is a knot with two balloons on it. It's a central atom with two atoms on it. And the third one is an atom with three bonded atoms, and the last one's an atom with four bonded atoms. So there are four pairs of electrons in the last example, and in each case, the balloons, the pairs of electrons are each balloon. The pairs are trying to stay away from each other. And you could do this for yourself. You could actually tie balloons to yourself, blow them up, try to make them about the same size, tie them together, and they will automatically fall into these shapes. And these shapes have names. The first shape, because it's just one balloon, it's a knot with a balloon. If you make a line from the knot to the end of the balloon, it's just a straight line, so that's a linear shape. Anytime you have two atoms, like fluorine bound to fluorine in fluorine gas, that's a linear shape. Any two atoms bound together will always be linear. There's nothing to figure out here. But in the second case, we have a central atom, the knot, bound to two balloons, two bonded atoms in this case, that represent pairs of electrons that are trying to separate away from each other. And the best way for two pairs of electrons to spread out as far apart as possible is in 180 degrees away from each other. So the two oxygens are as far apart away from each other as possible and still linked to the carbon. You'll notice I've ignored the fact that they are bound with double bonds. We're going to treat them as single pairs of electrons for now, at least in our heads. It won't change the general shape. In the third case, we have three balloons, three bonded atoms, and this forms a triangle of sorts, and we call this a trigonal shape, three sides, trigonal, trigon, and it's flat. If you put three balloons together, they would automatically form this flat, three-sided shape, trigonal planar, and you have to use both words. And an example of that would be boron trichloride. Boron does not have a lone pair, so it just has the three bonded chlorines on it that are all trying to get away from each other. The electrons are what are really trying to get away from each other, and they spread out, and each of those chlorines is bonded to the boron, and they're separated at an angle of 120 degrees each. So that's an AX3 type structure. The last structure shown here are four balloons attached to a central knot, and if you tied them together, they would automatically form this beautiful tetrahedron shape. It's a little pyramid with a stick coming up from the top, and you could rotate this any way you want. It's always going to be a three-sided pyramid with another piece coming straight up. And so do it for yourself if you have the balloons, and prove to yourself that this is the shape you would get. So this is a tetrahedral shape, and shown here is an example, CH4. You might have learned it as carbon tetrahydride. The organic chemistry accepted name for this molecule is methane. This is the main substituent of natural gas. Whatever, if you have a gas stove, this is what you're burning. If you're burning a Bunsen burner in the laboratory, this is the gas you are burning, methane. And you'll see that these four bonded hydrogens are all trying to get away from each other as best they can. They spread out into three dimensions and form this tetrahedron. But sometimes they're not all bonded atoms. We might have a case where some of these balloons actually represent lone pairs of electrons that don't have a bonded atom. So I've shown you pictures of three tetrahedrons. They're all tetrahedrons, a red, the green and white and the blue and white. It's a little hard to see the second balloon on the back of the blue and white one, but there are 4 balloons there. They each form a tetrahedron because they each have a parent shape of AX4, a central atom, the knot, with 4 balloons representing 4 pairs of electrons trying to get away from each other as best they can. They form tetrahedrons. And in the first case, well, that's the one we've already seen. It's a tetrahedron. The 4 bonded hydrogens are trying to spread out as best they can from each other, and you form this tetrahedron. And the way we represent this is by showing a dotted line, a dotted bond, meaning it's going back behind the plane of the paper or the plane of your computer. You know, if you're looking at the computer, it's a flat screen. We have one hydrogen that's going behind the screen, and we have that one right in the center on the bottom. That's coming forward, so you'll notice that's a little thicker. We tend to try to make it a triangular shaped bond almost. That represents a hydrogen coming forward out of the plane of your computer or your paper that you're looking at. And then the other 2 bonds are normal. They're within the plane of the paper or your computer screen. So that's an AX4. It's a normal tetrahedron. The parent shape is the final shape. AX4 is AX4. But in the second case, we have 3 bonded atoms, and one of those pairs of electrons is a lone pair. So we don't really see that when we're looking at molecules. And a classic example of this is ammonia, NH3. NH3 has a central atom, nitrogen, that has 3 bonded hydrogens and 1 lone pair. And those 3 hydrogens are not flat. They form a little pyramid. This is the same pyramid that makes up the bottom 3 bonded atoms of the regular tetrahedron. It is not, even though it's a little hard to see in this picture, those 3 balloons actually form a little pyramid. If I was able to hold it up, you could see that they form that pyramid, so that this is trigonal because it's 3-sided, just like before, but it's not flat. It's forming a pyramid. We call the shape trigonal pyramidal. It's also referred to simply as a trigonal pyramid. Either one would be accepted on any assignment that you do. And the last example is interesting. This one's 2 bonded pairs that are bonded to atoms, the blue ones, and 2 that are filled with lone pairs of electrons. In other words, there's no other atoms attached on those white balloons. They're just pairs of electrons. So we would still designate the parent structure as AX4, but the actual final structure in this case is AX2, E2. 2 are bonded, the X's, 2 are not bonded, the lone pairs, which we represent as E. But the total is still 4, they're still trying to get away from each other, and as a result, the 2 that we can see, the blue balloons, form a shape we just call simply bent. Not very technical, and the classic, most famous example by far is water, H2O. We have oxygen in the center, the center atom, with 2 bonded hydrogens, but oxygen also has 2 lone pairs of electrons that take up space. We can't really see them when we're looking at molecules, but they take up space. And as a result, the shape of the bond between H to O to H is bent. It's not linear like we see in the top with carbon dioxide, CO2. They're not flattened out. Those lone pairs of electrons push the bonded hydrogens down so that instead of being 180 degrees away from each other, they're pushed down closer to about 105 degrees away from each other. And you find these various relationships when there are lone pairs present. Now, if you look at the 4 top structures, the pink structures, they're all symmetric structures, completely symmetrical, as long as the central atom has only one kind of atom attached to it. Well, in the first case, we have a fluorine with a fluorine. There's only one thing attached to it, so it doesn't really matter. But it's symmetrical. CO2 is carbon bonded to 2 oxygens, which are very electronegative. So we actually have 2 very polar bonds around that central carbon. But what's interesting here is, and I'm going to draw this for you, is that if you were to look at the dipoles of this one's pointing this way, this one's pointing this way, and they completely cancel each other out. So this molecule, while it has two very polar bonds, is symmetrical around the central atom. Those two polar bonds cancel each other out. Likewise, with the third example, boron trifluoride, we have three very polar boron chloride bonds, but they're all pulling symmetrically away from the boron, and they cancel each other out as well. So this molecule is nonpolar, even though it has three quite polar bonds. Now, if I changed any one of those chlorines to something else, the molecule would not have all these canceled polar bonds anymore. They wouldn't cancel each other out, and the molecule would then have some polarity. It might be a little bit, it might be a lot. And in the last example, we have carbon with hydrogen, and they all have very tiny dipoles pointing towards the carbon. The carbon's a little more electronegative. If I put something much more electronegative as our outer atoms, like fluorine, we would have four large dipoles, but the fact is they're all pulling symmetrically or pushing symmetrically towards the carbon in the center, and therefore they all cancel each other out. But if I changed any one of those hydrogens to something else, the molecule would become polar again. If I changed, say, one of these to a fluorine, oops, let me get rid of that, sorry. Change this to a fluorine, suddenly we'd have this huge dipole here, and these other three are not going to cancel out this one, that's for sure. And now our molecule would be polar in this case. So if it's symmetrical around the central atom, it doesn't matter what atoms are, which kind of atom is attached. If all of those atoms, all of those outer atoms are the same outer atom, the molecule will be symmetrical, and the molecule will have no polarity, even though it might have some very polar individual bonds. But if you look at the last two examples, the trigonal pyramid in green and the bent in blue, those have a lone pair. They can never, ever be symmetrical. There is always an asymmetry in this molecule, and therefore, if you have polar bonds, like hydrogen to nitrogen, they'll actually add up, and you'll end up with an overall polarity, as it turns out in this case, pointing up. And in the case of water, we have a polar bond here and a polar bond here, and if you add those together, you actually have polarity in this direction. So anytime you have a lone pair, it's always going to be asymmetrical. It's always going to have some polarity. It might be a little bit, it might be a lot, but it will always be a little polar, at least. That's just a little note. Okay, so let's continue on with the rest of this unit. So let's look at some specific examples. We already talked about CO2. Let's break it down a little bit. If you were to draw carbon dioxide, you'll notice that the central atom has no lone pairs. It has two double bonds to two oxygens. We'll count those as two total bonded atoms. We're going to disregard the double bond, and we're trying to keep these electrons here as far apart as we can from these. And the best way to do that is by keeping them 180 degrees apart. It would be as if you were holding two things in your hands, and the best way to keep those things apart from one another is to hold your hands completely extended. So your chest is your central atom, and you're trying to hold two oxygens away from each other as far apart as possible, and you end up forming this straight line, a linear formation. That's an AX2, an A with two pairs of electrons on it, and we call that shape linear. We could also have the three bonded atoms. I showed you an example before with BCl3, which had boron with three singly bound chlorines, but no lone pairs. Here's a different example. This is formaldehyde. You probably heard that before. Maybe you didn't know what the structure was. It's carbon with two single bonds to hydrogens, and one double bond to a carbon, and there are no lone pairs on this carbon. There are lone pairs on the oxygen, but we're not looking at oxygen. We're only looking at the central atom. And because we have three things on this central atom, the best way to keep them apart is 180 degrees, a little Y-shaped molecule in this case. So it's Y-shaped, it's trigonal planar around this central atom, and I'm going to erase the rest of these notes. Trigonal planar. It's flat, but three points coming out of the center. Let's look at methane, CH4. We would draw a Lewis structure like this, and it looks flat, it looks four-sided, it almost looks like a diamond or a square shape, but that's not the actual shape of this molecule. This is a carbon with no lone pairs trying to keep four bonded pairs of electrons as far away from each other as possible. Well, the best way to do that, keeping these four pairs away, is to make them all go out and form a structure where each angle is 109.5 degrees. And you're going, why 109.5 degrees? Well, right now, if you draw a Lewis structure, you see that's a 90-degree angle between each of these. But it's flat. That is not reality. This is not what the molecule actually looks like. It's not a flat molecule. I'll draw it as if it was flat. It is not this shape, because there's lots of space up here and lots of space down here. This molecule will change, and what will happen is they'll spread out so that one of them will come forward, one of them will go back, and they'll take up more space this way. And as it turns out, the angle between any two of these is about 109.47 degrees, or about 109.5 degrees. And this allows the hydrogens to be even more spread out than if we just confine them to a flat area. And that shape is tetrahedron. Well, let's look at what that shape actually is. So here's the tetrahedral methane, CH4. And you can see the angle, what we call a dihedral angle, because this is a three-dimensional angle. It's not a flat angle in space. I'm sorry, this is not dihedral. That's an individual angle. But this also is 109.5 degrees. This is 109.5 degrees. That's 109.5 degrees. That one's 109.5 degrees. This one's 109.5 degrees. Any pair that you pick is going to be 109.5 degrees if all the atoms are the same kind of atom and they're all taking up the same amount of space. The hydrogens will spread out as much as possible. And so it will have that little pyramid on the bottom, but it will have one sticking out. And if I turn this sideways, I would get the same thing. I would see a different triangle formed on the bottom and a different one sticking up. And if you connect everything together, you get this tetrahedron shape. That's why it's called tetrahedral. Not because the molecule itself is tetrahedral, but if you connected everything in your head, all the bonded atoms, which are not connected in reality, but if you imagine the shape that connects them all, that would be a tetrahedron. That's where we get the name for this structure. The parent shape of this is an AX4, and the reality, the true form of this is also AX4 because all four pairs of electrons are with bonded atoms, in this case, 4 hydrogens. But if we look at a variation of the AX4 parent structure, in the case of ammonia, NH3 with a lone pair on the nitrogen, the lone pair still takes up space. And in fact, it actually takes up even more space than bonded pairs do. That you don't need to know for this course, but it does end up spreading them out, so this angle actually gets shrunk. It's a little less than 109.5 degrees. It's somewhere between 105 and 108 degrees. I don't remember the exact value, but it's small. It's squeezed a little tighter because this thing is actually very bulbous. It takes a lot of space up, but it's still essentially a tetrahedron. You just can't see the whole tetrahedron. You can only see the bottom part of it, which is still a pyramid. It's still a pyramid, but if you disregard that pair of electrons on the top and just focus on this shape, That's a three-sided pyramid. So being three-sided, it's trigonal, and being a pyramid, it's pyramidal. So an AX3E1 or an AX3E is the final shape. We call this a trigonal pyramid or trigonal pyramidal shape. It's just a distorted form of the tetrahedron that you can't see one of the parts of. And the last example in this set is water. Water has two lone pairs of electrons on the oxygen and two hydrogens on the oxygen. And you might have drawn it this way when you drew your Lewis structure. And there is absolutely nothing wrong with drawing a Lewis structure this way. It just doesn't represent the actual shape. The actual shape is not linear that you would see in your Lewis structure. You could even draw a Lewis structure that might look like this, where it looks like it's 90 degrees. Well, that's not the proper shape either. That's a fine Lewis structure. This is okay these are both fine for Lewis structures, but they are not good for showing shape. And this is why you'll frequently see water drawn as this bent molecule, because water has two pairs of electrons that are just taking up space. And you only really see the remaining part of the water when you're looking at water with some kind of chemical method, or maybe even a super high-powered scanning electron microscope, tunneling microscope that can actually see this. You'll see these bent molecules. You won't see the electrons. And it will just appear bent, even though the reality is it's really a tetrahedron that you can't see two parts of. And this is why we refer to the shape of water as bent. And this is an AX2E2 because its parent structure is AX4, four things trying to get away from each other, but two of them are lone pairs, the two E's, and two of them are bonded atoms, the two X's. So let's just review. We have the linear shape, which we find with AX2s and AX1s, but AX1s have to be linear. Two things bonded to one another have to be aligned. But in AX2, we have two bonded atoms and no lone pairs, and CO2 is one example. HCN, this is a cyanide gas. HCN has a carbon in the center bonded to a hydrogen and a nitrogen. You'll notice the nitrogen is in a triple bond, but we ignore that. It's just two bonded atoms and no lone pairs, and they will spread out to form a line. Trigonal planar, three things are trying to spread out. In this case, we have three bonded atoms and no lone pairs. Boron trifluoride is one example. Formaldehyde that we already talked about before is another example. Three atoms are trying to separate with their electrons in there, and neither central atom has a lone pair. Tetrahedral is when you have four bonded atoms to a central atom and no lone pairs. And methane that we already talked about is one example. Silicon tends to form four bonds just like carbon. It's in the same group on the periodic table, and they'll form four bonds quite frequently. And if you have four single bonds like this, those four single bonds will spread out. So here's silicon tetrachloride. The four chlorines spread out, and you end up forming a tetrahedron there as well. We also have the distorted tetrahedrons, the trigonal, pyramidal, and the bent. I've already talked about ammonia, NH3, with three bonded atoms and one lone pair. Phosphorus, right below nitrogen in the periodic table, behaves very similarly. It can also form three single bonds, or a double bond and a single bond, but in this case, three single bonds, and it has a lone pair taking up space. So you end up with this three-sided pyramid, a trigonal pyramid. That's the AX3E1. And finally, the bent, two are in bonds, two are lone pairs, that they all take up space, so it's really tetrahedron, but you only see the bent portion of the atoms in water, or sulfur difluoride in this case. Sulfur, again, will behave like oxygen. It will typically form two bonds. Though sulfur has a lot of other variants, it's bigger, so it can even make six bonds in other molecules, but in this case, it has 2 bonds to fluorines and 2 lone pairs, so it will also have that bent shape. And in summary, Vesper can predict a wide range of structures of covalent molecules. There are many exceptions. You're not responsible for any of those. That's more advanced. All the electron pairs, whether they're in bonds or in lone pairs, are mutually repulsive. They're all pushing away from each other to get as much space as possible so that they can all spread out. And as a result, you have these parent shapes, AX1 and 2, which are linear, AX3, trigonal planar, AX4, tetrahedral, as well as its distorted versions when some of those X's are really lone pairs that you can't see, but they take up space and make the other 2 X's keep the angles that they used to have. We could extend this to AX5, to AX6, all the way out to AX9. That's too advanced for this course, so we're not going to cover those. And as a result, the final shapes that you're going to look at, if there are lone pairs, will be distorted versions of the parent shapes. We can make distorted versions of a trigonal planar, for instance, by having it AX2 E1, but we're not going to talk about that in this course. It'll actually also end up being bent, but that's not part of the level in this course. And remember, lone pairs take up space too. In fact, they actually take up more space. You don't need to know they take up more space, but you definitely need to know that they take up some space, just like the bonded pairs. And you also have tables that you were given in your handouts. This shows you the AX1, AX2, and AX3 set, whether there are bonded atoms or electron pairs, and it lists all the sets. But you're only responsible for the 5 shapes we already talked about. This is a complete set of all the AX2s and all the AX3s, and shown here are all the AX4s, including one where you have 3 lone pairs, which would go back to being linear again, like the F2. I know I showed F2 as an AX1, so it actually can count as either way, depending on whether you're counting all the electron pairs or not. If you're interested, here's what happens when you have 5 ligands. We tend to see these with metal complexes. And here's what happens when you have 6 ligands, 6 outer atoms. You also see these in metal complexes, typically complexes with transition metals or intertransition metals. The really big metals, they use completely different rules. And here are some advanced rules. You are not responsible for any of them. As I mentioned, lone pairs are somewhat bigger than bonded pairs. They're not tethered in place by another bonded atom, so they kind of flop around and take up more space. Electropositive atoms, the ones that don't pull the electrons towards them as much, don't hold the electrons in and allow those electrons also to take up more space. That's called Bent's rule. And then double and triple bonds, because there are more electrons in a double bond or a triple bond than are in single bonds, they do actually take up a little more space, but not a whole count in the X count that we were doing before. But these are all advanced rules. You're not responsible for any of them. We have rules on radicals. Radicals are when you have single lone electrons instead of a lone pair. You have a single electron, and they give shapes that are somewhere between having no electrons and having 2 electrons. We have shapes that have more steric numbers or domain numbers bigger than 6, which have very unusual shapes we're not going to talk about in this class. Transition metals have a whole different set of rules to get those AX5, AX6, even some AX4 and AX7 and AX8, AX9 shapes. It's way beyond the scope of this class. We won't be talking about those. And heavy metals, the really big ones, can form unusual shapes. Here's one with a domain of 7, AX6E1, 6 plus 1 is 7. In some of these cases, they'll still form that shapes as if there were only 6, because there's just not enough room for the electrons to have their own space. And then you can even have some ones that are AX2E2 made with certain alkali earth metals like calcium, strontium, barium, fluorides. They might not actually be the shape you predicted. None of these are you responsible for. These are all very advanced. Don't worry about any of it. You could skip this completely, and with this, we'll stop here.